So we've been talking about Laplace's equation in Cartesian coordinates. I'd like to now talk about separation of variables techniques applied to spherical coordinates. Laplace's equation involves, of course, the Laplacian operator on the potential, and in spherical coordinates it has three terms. The term that involves derivatives with respect to r, derivatives with respect to theta, and derivatives with respect to phi. Theta is defined as the polar angle, so it's the angle between the r vector and the z-axis. Phi is the azimuthal angle, which can go all the way around to 2 pi. Theta can go from 0 to pi. If we write down this equation and look at it, we might want to consider cases where the potential has no phi dependence. In other words, it has symmetry around the z-axis. So when we do that, we can drop this term. So down here we have then the Laplacian with respect to v is the r-dependent term in terms of derivatives and the theta derivative term, and that equals 0. Given the equation here, we're going to use separation of variables. So we're going to assume that the potential can be written as a function of r, a function of theta, and this should be r comma theta because it depends on both r and theta. Taking the first derivatives, we will have the derivative with respect to r giving us r prime r, theta theta, and the derivative of v with respect to theta will just be r times capital theta prime. So if we substitute those into our Laplacian, you'll notice here that we have the first derivative with respect to r, we have the first derivative with respect to theta, so we can do that substitution. And in so doing, we end up with this term here. It will have theta on the outside of the derivatives. It'll have a term that is r-dependent, differentiated with respect to r. Similarly, we'll have the function that's inside these brackets here, differentiated with respect to theta, so there's no r dependence in here, and that will be equal to 0. So when we're done, we can multiply by this quantity right here, r squared over capital R, capital theta, and what that will do for us then is simplify these two equations. We'll have a term here which is r dependent only, and we'll have this term here which is theta dependent only, the sum of which is equal to 0. Well, this is similar to our capital X, capital Y equations that we got before, and so now we can consider that both terms are independent because you can set any value of r, any value of theta, and it still has to add up to 0. So we can set each equal to a constant, so we'll call one k. The other one will be equal to minus k. These, of course, have to add up to 0. If we let this one be plus k and this one be minus k, k minus k equals 0. We can change our partial derivatives to full derivatives, and that's what I've done up here because it's working on factors which only depend on r, or in this case, theta. So the separated equation will look like this, and now we do something that is very clever. We say this is equal to L times L plus 1. This is our k. And the minus k will be right here, minus L times L plus 1. The reason we do that is looking ahead where the theta equations are going to be dependent upon this L, likewise the r equations. Let's repeat. Here's our two equations equaling the plus k and the minus k. We take this equation here and multiply by r sub r, which will cancel this term here, and then we'll have an r of r over here. We expand the derivative, so we expand this derivative of a product. And so we end up with this equation right here, which is the differential equation for the r function, capital R. Well, this has a name. It's the Frobenius equation. We can use Mathematica to solve it, which is certainly a lot easier than the solution you have to do by hand. So we'll use dsolve to do that. Here's the program. First of all, in order to simplify our dsolve process, we can make assumptions about L. L is this thing that looks like a 1, but it's really an L. It's greater than 0. It's a member of the integer set, and the same goes for R. R is a real variable and is greater than 0. the heart of this is this expression right here, which is solving the differential equation, which is right here. This is the whole differential equation. We're solving that for capital R, and the variable is little r. So doing that and extracting the solution, we end up with this being the capital R of R, where this is L, this is 1. This is 1, this is L. There's two constants of integration, and so when we put these all together, we can write them in terms of constants a and b like this. So we have R of R is equaling capital A, R to the nth power, plus b, R to the minus L plus 1. So this is the radial equation for our Laplace's equation. Now the angular function we can also put into a form that is reasonable. It's this one right here. You'll notice that it again has our L times L plus 1. So when we're finished, we're going to have an equation that depends on L. We're going to let x be the cosine of theta, and so when we do that, we have that the derivative with respect to theta is equal to minus sine of theta d dx. So when we put this into the differential equation turns into a function of x, and so this is the x-dependent differential equation. This has a common name. This is Legendre's equation, and there are very difficult, lengthy routes to the solutions, but they take on the following form for different values of L. And these solutions are really where we get this requirement that k be L times L plus 1, and L is an integer. So let's use Mathematica to just solve this equation, see if it can do it. So here's our differential equation. It's exactly equal to what we had before. So if you take this equation here, you can see the terms right here. Here's our assumptions in terms of the value of L is positive, and it's a member of the integer set, and R is real and greater than 0. So putting those in, we can solve for the equation. So this would be our funny theta. So this is our funny theta of theta is equal to this. So two constants again, and we end up with special functions, namely the Legendre function with a capital P as a function of the integer L and the parameter x, plus another Legendre polynomial or Legendre function, which is Q, as a function of the same variables, L and x. This is our solution, and just to remind you, that symbol there is in fact L. Okay, so we're going to get rid of the q's. The Legendre q functions are called the Legendre functions of the second kind. They have complex infinities at x equal plus or minus I. We don't want that, so we set C2 equal to 0. That eliminates then the q Legendre functions from the solution. For C1, we're just going to call it CC and define then this g of x is equal to CC times the Legendre polynomial. These are polynomials, by the way. L and x are the parameters. These are called the Legendre polynomials of the first kind, and usually because these are so common, we call them the Legendre polynomials. Well, let's look at a few. The normalization used here is that this CC is equal to 1. So we're going to write them first in terms of an x variable. Remember, this is cosine theta. And so we will write p sub nx is equal to this quantity here, the Legendre polynomial. This is the order of the Legendre polynomial, which is equal to L, by the way, and x is the cosine theta. We'll also write it as this notation here. The L equals 0, L equal 1, L equal 2 polynomials in x are shown here. And Mathematica has a full understanding and record of what these are, and so they just simply come out as you can see here. And these can keep going on. And you'll notice that as you increase the order, these equations get more and more terms in representing. And these are polynomials, in this case of x. If we put in x equal cosine theta, then you'll notice that all we've done is replaced x with cosine theta, and these would be the Legendre polynomials as a function of cosine theta, or you could just say theta if you wish. those are the same equations that you have over here, except we've replaced x with cosine theta. This will be somewhat circular because we found this to be a solution, but let's just take this function g of x, the CC is equal to 1, and put it into the equation for the angular part of the differential equation. So all we're going to do is evaluate the left-hand side of the theta equation with this particular solution put in. So this will hold for any L, and we have to simplify the answer, but what we get is 0. In this case here, then, it's true for all orders of the Legendre polynomials. The expression for the differential equation does give us, in fact, 0. You've seen these various notations. This is a common one for the nth order Legendre polynomial, just a p without any notation. This is the same thing given in terms of x, and this is the same thing given in terms of theta. We'll use those interchangeably. Let's see what they look like. Here we're going to plot them in terms of x, so we'll plot them versus x going from -1 to +1. And this is the first Legendre polynomial, which you see is a constant because this was equal to 1. This equation here was equal to x, so you can see that it just has a linear curve, and so on. So you go to the second, the third order, fourth order, fifth order, and so on. So let's take a look at some of the properties of the Legendre polynomials. I list them here. One of the simplest ones is that if you count the number of intercepts with the y-axis, it's actually equal to m. So if we take the silly one here of 0, call that even, you can see that they reflect each other about this axis. If we go to an odd one, then down here you see that if m is odd, then at a given x, if you mirror it, you get minus the value. So that occurs here. You can see that if you go to x equal 1 and then go to x minus 1, we change sign. We have the same value, but it changes sign. Over here we have even, and you can see that it's symmetric about this axis here. All the even have that property. So here's 4, you can see that it mirrors about this axis. In contrast, if it's odd, then you basically flip the sign so that this is equal to minus this value here. So if you go right here and go roughly here, you get the opposite sign. If you go to x equal 1, it will always equal 1 for all of these. So if you go out here, you get a 1, here you get a 1, here you get a 1, and so on. So at x equal 1, all of the polynomials are equal to 1. Well, this is probably the most important result, and that is the fact that these two functions are orthogonal. If we have different n, then the integral is 0. If we have m equals n, we get a non-zero value. The expression here simplifies to this Kronecker delta function, so that if m equals n, this is equal to 1, and so the result of that integral is 2 over 2m plus 1. If m is not equal to n, you get 0. So that's an important result that we'll need to use later. Well, let's plot these same functions as a function of theta. We write them as the Legendre polynomial with respect to cosine theta. This is the Mathematica expression. They look very similar, except they have more resemblance to the angular functions that we know of. If you remember, this is equal to 1, the 0th order. This is equal to x, which is cosine theta, and that's what you see here. This is theta equals 0. This is theta equal pi. And so you have the cosine of pi, and so on. You have linear combinations of powers of x or cosine theta. So that's how these come about. This is not very helpful, but here they are plotted again as a function of x. This is the x version. This over here is the cosine theta version, and if you plot them all at once, you can see what's going on here. But basically, if you take this one up here, this is I equals 0. Same thing over here, I equals 0. If we take I equals 1, and that corresponds to this one right here, to this curve right here. So it's not useful, but it's kind of pretty. Well, a simple application of using the Legendre polynomials has to do with problems where you have a charge distribution on a surface of a sphere that is dependent on the angle theta. We can use a polar plot to see how this looks like, and here we start with a spherical radius equal to 1, and the corresponding Legendre polynomial that will give you this is p0, which itself is equal to 1. So what we can do is plot a cut through the 3D charge distribution at some constant phi, and so we'll take phi equals 0. We can then plot some angular function that involves Legendre polynomials. So for example, the first one, L equal 1, and then give it an amplitude, here 0.2, and plot 1 plus the Legendre polynomial times this amplitude. So there should be an amplitude factor right here. So here it is right here. Here's the 1 plus 0.2 times the Legendre polynomial. The curly bracket says plot the polar plot of 1, and then plot this one right here. So here we're going to go from theta equals 0 to pi, which is the normal range that you would expect for theta. So here's the two plots. The 1 is the green one. So that's the constant value of the polar plot function of theta. And then here's the extra term. Here's theta equals 0, and here's theta equal pi over here. Well, notice what happens is that you have a deviation, which is this function right here is the deviation from 1. And here you have a positive value. Over here you have a negative value here. So if you think of charge being distributed by this Legendre polynomial, the first L equal 1 polynomial, with some amplitude, 0.2, then the deviation here would represent that charge. So it's very thick here in the positive magnitude. Right here it's 0, and then over here it's negative, like that. So that's interesting, and it's helpful. But you might say that this really doesn't look right. This appears incomplete. And the reason is because this charge should be going around a sphere all the way around. So how do we get that? Well, you remember that we've chosen a particular phi. We chose this plane to be phi equals 0. So to generate the whole sphere of charge, we let the sphere and the charge distribution rotate about the z-axis. And phi will go from 0 to 2 pi, which will take this distribution, go all the way around, and come back to where it was. It's equivalent to plotting the distribution that I have here in this plane if I just go theta equals minus pi to pi. And so then we'll get the slice of the distribution, the entire picture. And that's what I show you here. So this plot then goes all the way around the sphere, and so here's lots of positive charge, here's lots of positive charge, here's a lot of negative charge, and then right here, right in the middle of the sphere, we have 0 charge. So that particular charge distribution would be an interesting one to look at. It's pretty clear that at least outside of the sphere you have something that might look like a dipole. So positive charge here, minus charge here, at least a long distance away. The difference then between these two curves is the behavior of the theta-dependent function over the surface of the sphere, and that's what I mean by these deviations right here. Here's another one. This happens to be taking the 10th order Legendre polynomial, and I've done the same thing. I've used the same amplitude. And what you see is that you have a distribution that wiggles because that's the 10th order Legendre polynomial behavior. It oscillates back and forth, and you'll notice, for example, that if you go from 0 to pi, you have symmetry in the deviation from the circle. Here you have negative charge, here you have positive charge. And so that's the 10th order version of the same problem. Another example, and I say pay attention because this equation right here is the sine squared equation in terms of cosine. So this is the half angle formula. But if you look at this is P0, the 1. This is P1, cosine theta. So we can represent this sine squared function as equal to this combination of Legendre polynomials. And here again is how those are defined. So now if we plot, in this case I've used a 0.1 for the amplitude. If we plot our sphere, which is the green one, that's our 1, and we plot 1 plus 0.1 times the Legendre polynomial terms. Here's the 0 term, here's the L equal 1 term. And we'll just jump to the conclusion that if we go minus pi to pi, we generate the whole problem. And so what you see here then, if this is the z-axis, we have sine squared of theta equals 0, 0, which we expect. If we go to pi, then we'll have the maximum, which is right here. And so here would be a bunch of positive charge, and then it would go to 0 right here. So this doesn't look like a dipole, but it does look like it has a lot more positive charge here than here. And we're going to take this particular angular distribution for the charge density and actually find the potential inside the sphere and outside the sphere. That'll be in a later talk. So now we want to talk about the combined solution. So remember, we found an R and we found this theta in terms of these Legendre polynomials. So for a given L, the potential would be written as our product of the R and theta equations. Here's our R, capital R. Here's our capital theta. And so this is the general solution for a single L. But you remember, just as we did in the Cartesian coordinates, because the Laplace equation is linear, the solution of a linear combination is allowed. And that gives us the most general solution, which is shown here. So we've summed from L equals 0 to infinity of the product equation. This is R sub L, this is theta sub L, as a function of little r and a function of theta. And so that gives us the most general solution. So if we start here, then the trick is we have to have a strategy. We want to eliminate as many terms as possible. And so the first thing to do is to see if you can use the boundary conditions to simplify the R equation. So if you can see that if a particular range of R makes this blow up, then you want to eliminate it. So for example, looking at R equals 0 or R equals infinity might allow you to eliminate terms. Well, I'll give you a hint. If you're inside the sphere, then you don't want to have R equals 0 and this term right here, because you'll have 1 over R to the 1, for example, at L equals 0. And so that's going to blow up, so you'll set B equal to 0. There's several other tricks that you can use, but those are the dominant ones. In terms of the theta equation, quite often we're using the Fourier trick that's analogous to what we used before, but now we're going to use the Legendre polynomials rather than sines and cosines. So we use Fourier's trick with the boundary conditions, and if we can, we try to end up with a finite series in the Legendre polynomials. So sometimes you need an infinite series, and so you'll live with that. You'll get the coefficients by integration, so you'll find these coefficients, but in practice you'll evaluate a few terms, whatever you need to get a smooth, reliable solution.